Okay, we are now doing question number 11. A 2-kilogram object is released from rest from a height of 3 meters above Earth's surface. How much kinetic energy does the object have when it reaches a height of 1 meter? Okay, so the way we can do this is we can use our kinematic equations. Conservation of energy. So let's set up our initial energy. We have our gravitational potential energy, so our mass times our gravity times our height, plus our initial kinetic energy, which is 1/2 m v0 squared, which is equal to our mass times our gravity times our second height. So let's call the first height h1 and the second height h2, plus 1/2 times mass times velocity final squared. So really all we have to do is plug in numbers from here. So we have the mass of our object, it's 2 kilograms, so we have 2, and then gravity is 10 meters per second squared here, so 2 times 10 times h, the initial height, which is 3 meters above Earth's surface. So that's 2 times 10 times 3 is 60 joules in potential energy initially, plus 1/2 mass is 2 times the velocity, which is 0 because it starts at rest, so we do not have any kinetic energy initially, so we can just go ahead and cross that out. So then, go over to the other side to the final energy of the system. We have the mass, 2 kilograms, times the gravity, 10 meters per second squared, times the final height, and it wants to know how much kinetic energy the object has when it is at a height of 1 meter. So h is now 1, plus 1/2 m, which is 2 kilograms, velocity final squared. So let's just do some simplification. So we have 60 joules is equal to 20 joules plus velocity final squared. Plus 1/2 times the mass, 2 kilograms, velocity final squared. But the mass is 2, so that cancels out the 1/2, so the kinetic energy is going to be the same in magnitude to the velocity. So we have 60 joules is equal to 20 joules plus velocity final squared. So that we have 40 joules is equal to velocity final squared, which is, in this case, our final kinetic energy. So 1/2 mv final squared is equal to 40 joules, which is answer E. In addition to using the energy concept of conservation of energy, we could also use our kinematic equations to solve this problem. So we would use delta x is equal to v0 t plus 1/2 at squared. So just to make this a little easier, let's just assume down is positive right now. So that would make our delta x 2 meters, because we are not actually going to assume that down is positive. I'm not going to do that. So our delta x is going to be our x final, which is 1 meter, minus our x initial, which is 3 meters. So we have negative 2 meters for our delta x is equal to v naught t. V naught is 0, so that's just 0, plus 1/2 a, which is going to be negative 10, because our gravity, our acceleration is gravity, which in this situation is negative 10, t squared. So, if we simplify this a little bit, we have negative 2 is equal to negative 5 t squared, which means 2/5 is equal to t squared. So t, the time at which the object reaches a height of 1 meter after being dropped from rest from 3 meters is the positive square root of 2/5 seconds. We can then use this time in a second kinematic equation. V final is equal to V naught plus A t. So V final is equal to V naught, which is 0, plus A, which is negative 10, t times t. Okay, so our final velocity is equal to our initial velocity, which is 0, plus our acceleration, which is negative 10, times t, which is the square root of 2/5. So final velocity is equal to negative 10 times the square root of 2/5, which, if we just use our calculator to solve, the square root of 2/5 times negative 10, we get not such a nice number. Let's, okay, so our velocity final equals negative 10 times the square root of 2/5. We can then take this final velocity and just plug it back in to find the kinetic energy there. 1/2 times mass, which is still 2 kilograms, times velocity, which is now negative 10 times the square root of 2/5 squared. So, if we take this value, negative 10 times the square root of 2/5, and we square it, we get 40.